All right, so last class we left off where we were talking about Leuder's rule. So for certain ideal measurement procedures.
Hey, Joseph?
Yes?
Could you throw on the mic there?
It is on. It is on. It's on.
Oh, excellent, thank you.
Is it working now?
Yes, it is, thanks.
Oh. Okay. I just touched it and it started on, I guess. So, okay, we're going to talk about the Leuder's von Neumann postulate, which is that for certain ideal measurement procedures, the state after measurement for an observable A equals the sum over L, AL, pi L, where ALs are real as usual, and the pi L form a PVM, which means it's an orthogonal set of projections that span the Hilbert space. The state after measurement is rho prime equal to pi k rho pi k trace of rho pi k when outcome k is observed. Okay, so probably a better way to do this, if you'll allow me to erase this prime, I'll put a k here. Okay? So now the key point is that, so this is full stop. So I have the remark. If we describe the state without conditioning on the outcome, if we describe the system, I should say, without conditioning on the outcome, so conditioning here means post-selecting, then the final state is rho prime equal to a sum over k, probability of outcome k times rho k, which is just equal to the sum over k rho k. Well, let's write it. Sum over k pi k rho pi k. I guess we have two different scenarios. One is if we condition on the outcome, and the other is if we don't condition. So we can think of conditioning as post-selecting. So, Here what we're describing now is this scenario where we have our measurement device. And now that what previously was just dotted in, we're going to make this, we're going to now actually describing our measurement device in this way. So here's rho, and this is rho k or rho prime coming out. And here we have our needle pointing to different outcomes, which is, these are indexed by k. And then we have our light that tells us we got an outcome. The light is redundant because if the needle, assume the needle has a rest position, then the needle moving to a new position implies a measurement was observed. So the light is redundant, just to be clear about that. And this is our dial, which chooses the measurement. Chooses the measurement. And this is the outcome. So what happens is we repeat this many times, or say we should repeat it one time. Well, let's say we repeat it many times. So I do this thousands of times. The light goes off thousands of times. And then what do I do with these guys? Whatever gets spat out of this right-hand side. Well, I have two choices. Either I can keep every system that comes out irrespective of the outcome, and in fact stop keeping track of what outcome occurred at all, and just collect all the systems. Then I'm not conditioning this. I'm not conditioning. Conditioning means if I get outcome k equals 3, I keep the system. If I get a different outcome, I throw it away. So this is why you have to renormalize. This renormalization reflects the fact that you're throwing away systems. Reflects the fact that we are discarding systems. Which are elements of the ensemble. So we're choosing a sub-ensemble. Now the same thing happened in our analysis of classical measurement yesterday. Classically, if I do a measurement, the intersection of my indicator function with the probability density gives me a subset of the initial probability density, and that is not normalized to 1 anymore. So I have to renormalize because I'm describing the sub-ensemble of situations in which the outcome was a certain outcome was found. Emily?
How do you decide which interactions are described by this rule and which ones are described by unitary solution?
We're going to do that. So the question was, how do we decide which cases correspond to this postulate and which cases can be described by unitary evolution? So let's look at that right now. All right. So the question is this a new postulate? Or rather, the question is, when is this a new postulate? When is this recipe, prescription, implied by our existing axioms? Okay, and while I'm remembering this, there's something else I wanted to talk about, which is what? I lost it already. All right, it'll come back to me. Okay, so I'll tell you the answer and then I'll prove it to you. So the idea is that let's call this case 2. Let's call this case 2, and let's call this case 1. So I'm going to tell you equation 2 is implied by our current axioms. But equation 1 is a new postulate. New in the sense of new to quantum mechanics, not new in the sense of new to physics, because we've already seen that such a postulate was required just to Bayesian update your knowledge. So it's an old postulate, but it's new to the quantum formalism in the sense that it's not implied by our prior axioms. So let's look at what happens when we don't condition. I promised you guys examples, and I was going to do an example of Leuder's rule. Well, let me just answer my question, and then I'll give you an example. So, all right. So the answer then. So the proof of the derivation of 2. Okay, so the derivation of 2 is that, oh, right, that's what I know what the other thing was. Once we add this output to our measurement device, you realize that it's kind of functioning like a transformation device. The system comes in, the system comes out. And it's also kind of acting like a state preparation. I'm able to prepare certain states if I condition on the output, right? So I want to talk about how measurement is really just a transformation. So we can express measurement as a transformation. All right. So the derivation of 2 was like this. I'm not going to worry about degeneracy for now. So first, I'm going to imagine that we have our system crossed with our apparatus, pointer, and we're also going to have everything else in the universe. Okay, so we're going to have HS cross HA cross H environment. And then we have some system states. Suppose I'm just going to consider, okay, I'm not going to derive the general rule for non-degenerate cases. I'll just show you an example of how you get this phenomenon just with the non-degenerate model of two-level system. Okay, so we'll imagine our system state is some state psi. And then we have some apparatus state, which we'll just call the ready state. And we'll have, in our environment, we'll have some other state. What do you guys want to call it? Phi sub e, perfect. Very apt, good man. All right, here we go. So the goal is to do a measurement, okay? So we want to describe this. We want to describe a faithful measurement. Of up versus down. Which are elements of my system Hilbert space. Okay, so what does that faithful measurement means? It means there's going to be, we want a unitary that acts on psi cross ready cross phi e such that if psi really is up, then the ready state goes to pointer right. And we want, and if psi is equal to down, then we want the ready state of the pointer to go left. Now, if we demand no false positives for our ideal measurement, then we want down to be orthogonal to left. Did I say down? What am I saying? Oh yeah, sorry. Left to be orthogonal to right. Okay, then we're guaranteed, that's this guarantee, which guarantees distinguishability. In a single shot. In each trial or run of the experiment. Okay, so this constrains you. So these are constraints on u, which is some unitary operator. Okay. So that means we have u acting on up cross ready cross phi e is equal to up cross right cross phi e prime. So we're just letting phi e have changed somehow. Remember, by our purification theorem, we haven't constrained the dimension of this Hilbert space, so this can be, we can assume without loss of generality it's pure.
By writing that, you're assuming that U is a local evolution. I mean, in general, that should be should entangle somehow.
Well, that comes, you'll see that in the next step. So the next constraint is that U acting on down, cross ready, cross phi e is equal to down cross left times phi e double prime. So we allow the possibility that the environment gets disturbed in some different way in these two settings, and it turns out that won't matter. We're just including this just to be general. It actually has no impact except to prove to people who say, oh, well, maybe decoherence can solve this problem. You know, decoherence can't solve this problem. In fact, this is a model of decoherence. Okay, so now what? So these are constraints. Okay, so now we know that U is a linear operator, is unitary, and hence a linear operator. Okay, so that means that if psi is a superposition, an arbitrary superposition of up and down, then we create an entanglement. So the point is the entanglement is a necessary consequence of the fact that we wanted a unitary which actually does something useful, which is actually correlating the pointer with the state of the system.
So why do you care what the post-measurement state of the qubit is? Why are you restricting that to be up goes to up and down goes to down?
Sorry, we're trying to be, okay, so we in general, measurements can disturb. So I'm assuming this because we're interested in whether we can achieve this ideal scenario prescribed by Leuder's von Neumann. So granted, you can design measurements which don't satisfy these conditions. They can be faulty, they can not be faithful, or they can disturb the system state. So the system won't be left in an eigenstate of the outcome you observed. That's easy to do. We're trying to design a measurement which does leave the state in the eigenstate of the observable we achieve. So it's part of our desiderata. But it's thank you for asking. So the question was, why am I assuming that we have up here instead of up prime? Why don't I allow some disturbance to the system state just like I allowed a disturbance to the environment state? And that's a very good question because it brings out an issue, which is, look, we don't just want to get the probability right. We don't want to just measure alpha squared via this procedure. We are asking for a procedure which leaves the system in the state associated with the eigen outcome we measured. So that's why we demand this condition. Yeah?
This with something like what we did a few days ago where you're doing a Stern-Gerlach and you measure the spin by looking at the spatial degree.
This is exactly this. This is another, right.
Why are you justified to make that distinction? Because you couldn't resolve it physically, right? Like, why can't you have Jake discussed, why can't you have an arbitrary complex phase in front of the UL?
Okay, that's a good question. You want to add an overall phase. The overall phase is physically irrelevant, but but the question is, does it become a relative phase when you put in the superposition? The problem, well, U is only defined up to an overall phase physically, anyways. So the overall phase can't possibly matter. I don't know if that's an adequate answer to your question, but this ties in with something my grad students thinking about. So, but yeah, if you had some overall phase here, I suspect that that's not physical, but there's something bothering me, so I'm not entirely certain. So let me just think about it. Let's finish the discussion, and then we can revisit that if you feel like it's something we need to explore. Okay, so here's our superposition. Now the point is, by the linearity of Schrodinger evolution, we get then U acting on psi times ready times phi E is equal to alpha up right. Oh, I'm going to run out of room. Phi E prime plus beta down left cross phi E double prime. Let me move this up. Okay, so we've created a coherent superposition and an entanglement. Hence, it's a pure state, so we know it's entangled because it's correlated. So then, where am I? Oh, I did this wrong. I pressed the wrong button here, didn't I? No, I didn't. Okay, sorry. Sorry, I guess I shouldn't have moved that up yet. That's what confused me. So we're going diagonally down here. All right. Okay, so now the point is, if we ignore the apparatus and the environment, then we obtain rho s prime. We're going to define that as the trace over the apparatus times the trace over the environment of, okay, I'm going to need a shorthand. Let's call this state chi. call it chi prime because it's after the measurement. So the trace of chi prime. Okay, I'm writing this out explicitly, and then you can evaluate this, and what do you get? You get alpha squared up plus beta squared down. All right, and this is exactly what the von Neumann-Leuder's rule prescribes when we ignore the outcome. So I'm not even looking at the apparatus. I let the measurement interaction happen, then I ignore the apparatus. Essentially, I don't care what position the pointer pointed to. My state after measurement is still normalized because I haven't thrown away any systems. And this is exactly sum over k, pi k, rho, pi k, i.e. case 2. Okay? Yeah?
Referring to Jacob's question, if you don't fix, they have to go to up and the down go to down. Then you'll have something similar but with coherences, right? I mean, with non-diagonal terms of your estimate.
Yeah.
So, I mean, what you're defining by a faithful measurement is something that, as I measure the other degree of freedom, it gives me information of the one that I'm interested in.
Well, I mean, there's two. Yeah, sorry. Let's be clear. So there's two requirements we want to satisfy. So the first requirement is that when the needle points left, I know with certainty the state was the eigenstate up. Okay. So there's no possibility of it pointing left when I had some other input state. That's what I mean by faithful. And then what is it, Jacob? What Jacob brought up is the question about why am I requiring that the state isn't disturbed? Because it's possible to do this where the state is disturbed, but it's still faithful. So there's the retrodiction issue of what state was I given. So that's the first task of measurement, to correctly retrodict the preparation. And the second task, when we want to describe the state after measurement, is we can ask that the measurement not disturb the state. So if up goes in and I get up, I'm guaranteed to have the pure state up afterwards. That's a second requirement that's in addition to the faithful measurement requirement. And that's the non-disturbance or the non-destructive measurement requirement, also sometimes called just an ideal measurement. And that's what the textbooks talk about, that scenario. But it's, as I mentioned several times now, it's important to realize that in practice, measurements are often designed just to fulfill the first requirement, to retrodict something about the preparation. And they're often not designed to satisfy the second requirement, which is the Leuder's von Neumann rule, that the state indeed is left in an eigenstate of the observable that was measured. Yeah?
Is there something that needs to be said about left and left being orthogonal? I mean, you're saying the state of that box pointing to the left is orthogonal state of the box.
Yeah, so I'm imagining, so you have essentially the pointer position is described by some coherent state whose width is, 10 to the 10 orders of magnitude smaller than the distance between the pointer pointing left and the pointer pointing right. So if you imagine these are Gaussian states describing the positions of the pointers, the overlap is negligibly small.
So that negligibility, let's say something about how big the apparatus needs to be.
So the question is, what are the practical requirements to ensure that right and left are non-overlapping? And the answer is no. It doesn't make any conditions on the size of the apparatus. You can just do it with another spin-half particle. I can have my apparatus can be another spin-half particle. This won't be good because I can't easily read out another. I mean, I can easily look at a pointer, but I can't easily. The requirement of size is really so that we can talk about something that's macroscopic and we can knock on, right? Something that's clearly physically real and fixed. But no, you can just have two spin-half particles, and I can, the C0 gate of quantum information is just that. It's going to flip the second bit if and only if the first bit is pointing in one direction. And so, yeah, you can think, I mean, the word measurement becomes very loosely defined. You can think of it as a measurement, sure. I mean, the point is there's information about the first system in the second system. So you can call that a measurement if you want. There's no reason, no one could argue with you. It's not very practical unless you have some way of reading out that second spin. But of course, this is what people do in the labs over at IQC. They do these things, and then they transfer the information from a nuclear spin to an electron spin, and then they can read out the state of the electron spin using lasers. So even though it's just as small from our point of view, there's a more convenient interaction that can be manipulated. So I think it's totally fair to call it a measurement. I wanted to mention that what's happened here, notice that we started out the input state we imagined was some coherent superposition, a pure state of our system. And then the output state is this highly mixed state, assuming alpha and beta are somewhere in the interval 0, 1. So we've lost coherence. If we just remark, so I'll say this as a formal remark. We have lost coherence. We have lost the initial coherence. Okay, this is a very simple point you probably all know, but let's just make sure no one's missing this. The initial state, psi, if we write it out as a density operator, what we get is rho s prime plus alpha complex conjugate beta up, down, plus alpha bar beta down, up. So we get our final state that's been decohered plus these off-diagonal terms. So the measurement interaction, when we don't condition on the outcome, just removes these off-diagonal terms, which are, so the point is that these coherence terms these off-diagonal terms that represent coherence between up and down are destroyed or sent to zero, or what, I don't know, what killed off, whatever terminology you like, are eliminated. And then we're just left with this piece. So in particular, what happens is that we had a situation where we had trace, where we had basically we went from a pure state to a mixed state. Okay, so oftentimes you'll hear people talk about the environment measuring your system. So people kind of abuse the concept of measurement and talk about interactions with stray particles that you didn't have access to that spoiled your experiment. People call that's decoherence. People call that your system was measured by the environment. So what that means is not measurement in the sense of conditioning, but measurement in the sense of not conditioning. So remember, our measurement scenario had case 1 and case 2. Case 2 was where we don't condition on the outcome. Well, this exactly corresponds to the environment measuring or monitoring your system. The important point is the information about your system has kind of, I mean, this is very loosey-goosey terminology, but the information has flowed out of your system into the environment. And if you want to maintain coherent control of the system, you have to prevent that flow of information because it leads to a loss of coherence, which is a loss of signal.
So going back to what we were talking about yesterday, with this classical analogy to probability distributions and phase space, what's the analogy between the distinction between post conditions?
Yeah, okay, so this is a great question. The question was, yesterday we saw how the process of update, the update rule of measurement has an analog in classical probability theory, which is corresponding to conditioning on new information. And then the question is, well, what's the different? How is that analogy different in case 1 and case 2? So here's the answer. So in case 1, we get essentially exactly the classical analog. In case 2, we get something that's not classical. Okay, so in case 2, we have. So let's write this down. So remark. Case 1 corresponds. So case 1, which requires a new postulate, which requires a new case 1, which is not implied, by unitary dynamics. So it's actually inconsistent with unitary dynamics. Not implied by, or is inconsistent with unitary dynamics, has an analog in good old Bayesian update. And case 1 is the mystery for most quantum scientists, incorrectly. Case 2, however, does not have an analog. Case 2 is distinct from the classical analogy, is distinct from the classical case, from the Bayesian update, because the state is changed. The state changes. So classically, if I do a measurement and then I ignore which outcome I got, I haven't affected the system at all. My probability density rho goes to rho prime, which is equal to rho. But here we've actually we've lost coherence. Now, so the whole point is that one of the ways in which this classical analogy breaks down is that classically there's no way to distinguish between a coherent superposition and an incoherent superposition. So I can construct a classical model which models coherent superpositions. But if I do that, then I'm unable to distinguish between a notion of coherent and incoherent superposition. So what that means is that what this tells us is that quantum measurement necessarily disturbs the physical state of affairs. Okay, so classically, it's possible to have non-disturbing measurements. And quantumly, if we accept that the quantum state is not the physical state, then we find that physical state must be disturbed by the measurement. Emily?
Could you not have an analogy for case 2 in classical probability in the sense that you think of a larger probability distribution and then just marginalize over some part of it? Trace is similar to marginalizing.
That's really interesting. I'd have to think about that. Yeah.
So because this measurement is unitary, if we send in a
doesn't this force us to take the Everett interpretation? Because we could just as easily, instead of having the ready and right corresponding to our pointer, we could have that corresponding to our brains interpreting it. So unless we have to say that our brains aren't described by quantum mechanics, doesn't this force us to take the Everett interpretation?
I didn't understand the question. I know the answer, which is no, but I don't understand the question, so you have to repeat it.
If we start in a pure state
Mm-hmm.
of the entire environment apparatus and initial state,
Which is the situation here.
then we apply unitary to it, so the state afterwards is going to be also pure.
Right.
But so surely that means there's going to be some entanglement with that means so the state of the entire universe is going to still stay pure, meaning we do not get any, which is essentially the Everett interpretation.
No, the fact that the state of the universe is pure is fine in every interpretation. So yeah, I mean, saying that the quantum state of the universe is pure is not a statement that decides between interpretations.
It feels like we're going to get some sort of entanglement between.
Oh, there's definitely entanglement. I mean, this isn't it.
So the state of the pointer is going to end up in a superposition.
Yeah, the state of the pointer is in a superposition overall,
Yeah.
but not. But then when you, if we.
Why can't we use
What happens when you can observe the pointer in superposition?
if we observe the pointer, then surely our brains can access the pointer as well.
Yeah, but then you're best selected.
Yeah, your brain could be in phi e as far as I'm concerned, right? This is any other degree of freedom you care to describe. So yes, you are entangled with. I mean, yeah. I guess the Everettian view would be something like, well, I'm in both of these branches simultaneously, and then if I'm in this branch, I see right. If I'm in this branch, I see left. It's something like that. I mean, there's several flavors. I don't.
I mean, what would you say happens to your brain when you observe a pointer in a state like this?
The same thing that happens in 1850 when I observed a pointer, which is that my brain has some chemical process that encodes you saw the pointer left, and
Two different possible processes depending on the right and the left.
I mean, the
Which
unitary must
process
govern
does
the
it
evolution of your
undergo?
brain conditioned on the state of the pointer.
the unitary must.
I mean, this unitary we're applying to the entire universe must have some coupling between the state of the pointer and whatever is going on inside.
No. Remember, my working hypothesis is that the description of reality provided by this mathematical object is not a complete description of physical reality. It's just some mnemonic. It's a tool. It's like a probability density. So I don't demand that this give me an exact description of what's going on because I don't expect it to. So I don't have to explain, based using quantum mechanics, why my brain is in a particular state, because I don't think quantum mechanics does that. And in fact, when you try and demand that quantum mechanics does that, that's when you run into problems. So there are very deep issues here to explore, and measurement has puzzled people for years, and I mean, I don't want to quell discussion, but at the same time, I do want to make progress. So, okay, let me take like one or two more questions if there are.
So going back to the classical case, what is the process that actually corresponds to? So I mean, I can see how you would measure a probability distribution, assuming that you're considering that to correspond to some box that generates particles or something. But what corresponds to doing the measurement that tells you take this window of the density distribution?
Oh, so that's a conditional statement. So you can't control what outcome you get. If you have a probability distribution that has support over several possible outcomes, you can't control which outcome you get classically or quantumly because you don't know what outcome you're going to get. That's the whole premise. So if you want to the only way you can control the outcome is to just throw away systems that don't give you the outcome you want. That's the discarding. So I repeat the experiment. If I don't get the outcome I want, I just throw it away. I repeat the experiment, and then, I got the outcome I wanted. Now I'm going to save that system. And then I can keep repeating it until I get thousands of systems that satisfy that condition I was interested in. Is that?
Well, okay, yeah. Now I have another problem with that, though, which is that, so it seems like in the first case, the distribution describes the thing creating the things you're measuring.
Mm-hmm.
And now that's no longer the case. Now it describes some subset of the particles that are actually generated.
You mean this device here, or do you mean the preparation that created rho?
The device off to the left.
Yeah. Okay. Yeah. Exactly. No, the device that created rho doesn't care about what outcome k you're going to get, obviously. So yeah, I think there's something fishy about your question. I think that will require some dialogue. So let's defer that till after class. There's a question at the back.
Sorry, do you mind covering contextuality at some point in regards to measurement?
Sure. It's a great topic. I'll see if I can squeeze it in. Yeah.
In practice, I will typically end up doing something that's in case 1 or 2. I mean, I'll have something. Imagine something is a bunch of energy I get state, but I can only measure the energy to be between some window.
Oh, that's a degenerate measurement. Yeah, yeah. So you're considering about, so that's when, if I understand the question is, how can I create a situation where my measurement is coarse over some set of states? And that would correspond to the situation when pi k is not rank 1, which I did not illustrate explicitly, but is,
Even if it is rank 1, wouldn't, like, say, it's like, I don't know, you see the classical case, your measurement apparatus is not perfect, so you can't really tell afterwards whether this eigen state of energy or one slightly above it or one slightly above it.
yeah, that's fine. I mean, that's what happens. I mean, yeah, you can violate any of these assumptions and create a measurement model that's less ideal. And then you get more complicated situations. But I mean, let's look at the extreme case, and then everything else is kind of an intermediate situation. I mean, yeah, there is a very rich set of, I mean, if you're interested in like theory of experiments and how actual devices work, then there's all kinds of imperfections that one has to account for. All right, last question, Andres.
No, with respect to Emily's question about the marginalization of your probability in classical case,
Mm-hmm.
which can be resembled to the second case here. But I mean, in the classical case, if you have your conditional probability, right, and you take the probability of an outcome without conditioning, right? If you do this sum that you have here, you recover your whole probability.
Exactly.
Right? But in this case, we're not recovering the same density matrix. That's the
Right.
That's the fundamental difference between both.
But the difference is that the point is that you allow the probability to evolve, you know, according to your laws of motion over the whole distribution. But then when you can like marginalize over just a single subsystem, you will get something that looks a lot like this.
I think, well, from Emily's question, I think, so, I mean, I've told you about we're writing this response to PBR paper right now. And one of the tricks we do is that we actually encode information about the state in an inaccessible degree of freedom, which when you marginalize over that inaccessible degree of freedom, you recover kind of behaviors that look independent and so on. But so what I'm trying to get at is there might be clever ways to force a classical model to have some kind of analogous property where there's the measurement has had an impact on the physical state through some disturbance relation, which isn't detectable under accessible measurement. So I think that's...
You model the interaction with the measurement device as, you know, an evolving probability distribution, including the measurement device in your subspace. And then you then trace out or marginalize over that and just look at the individual system. Effectively, we'll still get something a bit like this.
Yeah, I can imagine that working. So let's take that conversation offline, though, because that's a bit specialized. But I should send you a copy of our draft, actually. OK, so let's move on to the next topic. So I conveniently have an outline up here. So update rule, conditional versus non-conditional, done. Is it an independent postulate? Yes, in the case of 1, but not in the case 2. And then the claim was that independent postulate is really just a classical Bayesian update, so it's not that mysterious. State update, no, Neumark's theorem, POVMs, connection with decoherence we covered already. Express measurement, so I get glare, as a transformation. All right, that's all good stuff. All right, so Neumark's theorem. So Neumark is sometimes written Neumark. I might have alluded to this already, but I don't think I did it carefully. So, I mean, here the point is that, okay, so first, recall, well, I don't need to remind you about our axiom. Okay, we have POVMs. All right, let's just do this. So given, okay, I'm just going to do the discrete case because we don't want to, well, I'm not going to require you to learn measure theory. So let's just talk about the discrete case means that our set of outcomes is indexed by a discrete variable. So it's possible in quantum mechanics to have continuous outcome sets, even though we have a separable Hilbert space. But we'll just worry about the discrete set of outcomes, because mathematically it captures all of the issues without having the mathematical overhead of measure theory. So given a discrete POVM, here, I'm going to say discrete case only. What I'm trying to say is Neumark did this in full generality. We're only going to look at a special case, the discrete case. Given a discrete POVM, which is a set of operators EK, and remember the EKs have to sum to identity, and each one is non-negative. Where we have the Born rule, the probability of outcome K is equal to the trace of rho EK. We can always what? So I told you already that if you have a density matrix, an arbitrary mixed quantum state, you can always create that state by creating an entanglement between your system and your apparatus, and then your system and your ancilla, and then tracing over the ancilla. So any mathematical object that is a density operator can be realized physically in terms of our fundamental axioms of quantum mechanics. Similarly, we saw that a generalized transformation was something given by a Krauss operator sum decomposition. And then we saw the Stein-Spring dilation theorem, which told us that any mathematical object that corresponds to a Krauss operator decomposition can be realized physically in terms of a unitary acting on your system and an ancilla with the ancilla prepared in some state. And then we trace out the ancilla, and we create any completely positive map you want. So that means that the mathematical set corresponds to a physical set if we accept the ideal axioms as being, realizable. So the same situation holds for POVMs. So if I have any POVM EK, which is a mathematical object, can I realize it physically? Well, yes, you can realize it physically. You can always realize it via So this is, how do you want to divide up your Hilbert space? Let's call it HS cross H. Now let's do A and B. HA, HB. And then we have identity on A. U isn't. For some U, which is an element of the which is a unitary operator, which is an element of HA cross HB. So U is an interaction between my system and my ancilla B. This is linear operators. Phi is a state, so it's a density operator on HB. And here pi k is a PVM on HB. Okay, so I imagined I had this mathematical object which generates statistics via the Born rule. I can always create a physical system where I take the input state. So this is what's going on inside this box. Okay, I can take any POVM you want, and I can find a way to realize it in terms of projective measurement only on the ancilla. Remember, this is von Neumann's indirect measurement model, where we couple the system with the apparatus via some unitary. The apparatus is prepared in some state, and then we just measure the apparatus, and then we get the statistics for the probability of an outcome that matches the POVM element. Sure. That's a good idea. Okay, so I'll draw a circuit diagram for this, just see what it looks like. So if you are given EK, you can realize it. You can make this measurement. You can realize this measurement as follows. Rho U phi rho k, and this is a measurement pi k.
So on that line where you have the probability of outcome case, that's a number, but on the right hand side you have an operator, you have a partial trace over B. So should there be another trace?
Yeah. Yeah. Thanks. Sorry, so we have to remove this subscript. That was incorrect. That subscript comes in when we want to talk about the state update rule, which we'll get to next. Okay, so this is great. So not only can we realize any POVM in the lab, which is nice to know that I can produce the Born rule statistics associated with any POVM if I have unitary control over another ancilla system and how it couples to my system of interest. Okay. Not only that, but moreover, I can always realize it where I can do some arbitrary projective measurement, possibly destructive, on the second system, and get an output state rho k, which satisfies certain reasonable properties. So now the question is now, what is rho k? So in other words, what is the state you get after performing some arbitrary, so the state update rule for POVMs is the next question. Okay, so now this is actually very subtle. I certainly have confused myself thinking about this in the not too distant past. So let's go over this a bit slowly. And I might actually just check my notes. Yeah.
What is that? What is the bottom right corner of the diagram where you have the projection?
So typically, so boxes mean transformations, and this means measurement. So this corresponds to essentially sweeping the measurement under the rug, right? Literally. So we put the measurement on a system we don't care about anymore, and it makes it a cleaner way to think about things. So what is rho k? So you know what? I forgot to give an example of Leuder's rule in the case where pi k is not rank 1. And so maybe we can include that in a tutorial or assignment or something. Okay. So yeah, I have an example worked out, and then we can go through that. Okay, so what is pi k? So the state after measurement. So it turns out that, so first remark, there is more than one way to skin a cat, so to speak. There is more, I mean, more than one way sounds, it's non-unique. So what I want to say is non-unique. I want to say that oh, fine, I'll say it. There is more than one way. There is more than one way to realize a POVM. In particular, the final state rho k is not uniquely determined by the POVM but is determined via a complete description of the experiment. Of how the procedure, the measurement procedure, is performed in the extended Hilbert space. Okay, so it doesn't make sense to say, okay, I did this POVM, now here's the state you get after the measurement. There is no unique state. It depends how you do the measurement. So in the case of Leuder's rule, it's clear there's no ambiguity. Rho k is exactly prescribed by equation 1. In the case of a POVM element, there's more than one way to realize it. There's more than one way to Neumark dilate it. And so therefore, EK, the POVM does not determine rho k. You have to tell me how you implemented that POVM.
The unitary you have here is arbitrary?
This is an existence theorem. This says that there exists, this is like a there exists. I could, maybe a better way to say this would have been, given a discrete POVM of this form, there exists a unitary, a state, and a PVM on HB such that we reproduce the Born rule statistics. And in fact, it's a non-unique existence theorem. There exists many choices of U and phi and pi k that give you the same statistics. And each of those choices generally gives you a different state rho k conditioned on the measurement. Yeah, so EK would correspond to trace over B. Trace over B of this expression. Yeah, maybe I should make that explicit, shouldn't I? Yeah. Oh, you can't see. All right. So yeah, I think that we're gonna. Yeah. So yeah, I think that EK. So for Neumark's theorem, you would have EK is equal to the trace over B of that whole expression. No, that's not gonna work.
EK in terms of a trace of something is defined via the probability like this, right? I mean, it's the same as how you define the cross operators. You cannot take the AK as.
Well, here, anyways, you know what? The next step in this discussion is actually to do the calculation we need to figure this out. So let's just do it. All right, let's look at this explicitly. So here's the thing. So given some choice of u, phi, and pi k, we have that rho goes to rho k, which is equal to the trace over B of identity cross pi k u rho cross phi u dagger identity cross pi k. And then, oh, right, I remember so the trick to get EK, I remember now. So let's just remark that identity cross pi is a projector. So this times this is itself. So we have trace over B. This is equal to the trace over B of identity. And then what we're going to do is going to bring this u over here. We have u dagger identity cross pi k rho cross phi. And I missed a u somewhere. There's a u here. Now we're doing a partial trace. Let's choose okay, let's define what am I waiting for? Ah, thank you, that's right. Yeah, that's correct. In fact, I think this is exactly the mistake that confused me last time. Thanks for catching that. U dagger goes here, and then we can't do that.
You can put the projector in the other side. That's okay.
Just the projector. Right, so the cyclic property of the trace does not work for the partial trace, right?
I mean, it works for local operators like identity of pi times pi k, you can move it. But unitary, you cannot move it.
Right. Okay, so let's define phi equals 0, and then we're going to use a basis j to evaluate partial trace. Okay, so then we have rho k is equal to a sum over j identity cross pi k well, the identity drops out, obviously. So we have j pi k u acting on rho cross 0 u dagger yeah, because this is going to be a delta function. Oh, that's only a delta function if we assume that. Yeah, I don't want to, though. I don't want to because I want to create a symmetric expression.
So the function, I mean,
So-
rho is in AK, right? So the zero can go to the left.
I know.
So
Yeah. So now what we do is we define. Is this a good spot to write? You guys can all. Oh, you can't see. Here, I'll move over here. Okay, so I'll continue over here. So now what we're going to do is we're going to define Krauss operators. Okay, so we're going to define an operator mk comma j equal to j pi k u 0. And then we get that rho goes to rho k, which is equal to sum over j mk comma j rho mk comma j dagger. And we want to normalize. Where's my normalization? Well, this is a subnormalized state. That's fine. We'll have it subnormalized. Okay, so this is our update rule, where mkj depends on the projector, the unitary, and the initial state of my apparatus. So these are my freedoms. And we have ek is equal to a sum over j mkj dagger mkj. And then I want you to remark that sum over k and j of mkj dagger mkj is equal to identity which implies this is a Krauss operator sum decomposition. In fact, it's a CP-TP map. Okay, so if we sum over k, we get a CP-TP map defined by Krauss operators mkj, and conditioned on k, conditioned on one outcome, some outcome k, then we don't sum over k, we get a CP map. A CP map for a particular k. Okay, this is a bad notation because here I'm talking about a map where we're just imagining k fixed. And here we're imagining for all k. So this explains how we can think of this measurement box as a transformation, and it's a trace-preserving transformation if we don't condition on the outcome, and it's a non-trace-preserving completely positive map if we do condition on the outcome, because we're throwing away systems that didn't give the right outcome, just like in classical probability theory. And so let me just now point out something, which is that this is what confused me last time. I did this, which was just 8 months ago in a different class. Most textbooks, in fact, all references I can find, tell you that the most general update rule, okay, so most sources, if not all sources, most if not all sources give you, as the most general rule, is that rho goes to rho k, which is equal to some mk rho mk dagger, where there's no extra sum over j. And they say this is the most general transformation. Now, it seems to me that you can't get rid of this index, j, unless you assume that the projectors are rank 1. So I don't see how to get rid of the sum over j unless the pi k are rank 1 projectors. So I don't know what the resolution of this dilemma is. I don't know if most people just haven't worried about the case where pi k is not rank 1, and so they say that's the most general rule. Another possibility is that somehow Neumark's theorem promises you that there exists a dilation in terms of rank 1 projectors, which I doubt that's the case, but it's possible. And so this is kind of an open question for me. I'm not promising you it's an open question for the community. It's an open question for me. In other words, is it possible to get rid of that index without losing any generality, that sum over j? So, I'll pose that as a bonus problem. If anyone can figure this out, let me know, because I'm interested to make sure I understand this as thoroughly as I'd like to. Yeah. Okay, so we all are probably pretty hungry. So are there any questions about, is there anything we didn't touch? The connect, yeah, express, okay, we did it all, great. So now, any questions about this? All right, that's a fair amount of silence then. Have a good weekend, and I'll see you on Monday.